Starting chapter 10 here in PreCalc, and we are looking at this lesson, sequences and summation notation. This is something you may have looked at in Algebra 2, so maybe this is review, maybe it needs to just be refreshed greatly in our minds, but we'll go through these. The nice thing with chapter 10, I was thrilled to see when I went to set it up again, is that each lesson is a front and back page of notes, and that's it. So hopefully that's a high note to look at here at the end of the year. So definition of a sequence. We're looking at a sequence. An infinite sequence is a function whose domain is a set of positive integers, and the terms are represented by these terms a1, a2, a3, a4, and it goes on through an, and it keeps going because infinite means it doesn't stop. And a sequence whose domain consists of only the first n positive integers, so they have to give you that number of n, that's a finite sequence because finite means it ends. So the first two we're going to look at, we're just writing the first four terms of each sequence, so that means we're looking at a couple finite sequences here to start with. So when they give you a sequence, they need to give you a rule. You'll notice on number 1 I have a to the n, or I shouldn't even say to the n, a of sub n equals 1/3 to the n power. So a sub n is a notation, and then on the other side 1/3 to the n power is actually our operational side. So we replace n with what term we're looking at. So if I'm looking at the first term of a, so a sub 1 is the first term, and it simply means I'm going to have 1/3, and I plug in 1 again for this n. So my first term, 1/3 to the first power, is just 1/3. So my a sub 2 means my second term, and I get 1/3 to the second power. 1 to the second power is 1, 3 to the second power is 9. My a sub 3 is my third term of my sequence, so I have 1/3 to the third power. So 1 to the third power, 1 times 1 times 1 is 1. 3 to the third power, 3 times 3 times 3 is 27. And I'm going to the fourth term, so a sub 4 would be my last term I'm finding in this finite sequence. And I have 1/3 to the fourth power. So 1 to the fourth power is 1 times 1 times 1 times 1, which is still 1. 3 to the fourth power is 3 times 3 times 3 times 3, which will be 81. So my answer here, the first four terms, are these four fractions right here, 1/3, 1/9, 1/27, and 181. And we like to have that symbol with it, like a sub 1, a sub 2, a sub 3, a sub 4, to tell which term in the sequence we're talking about. So let's try another finite sequence here. This one has a slightly more complicated rule. Remember, the a sub n on the left is simply a organizational or identifier, and then on the right side is going to be our operational. So we're going to start out again with a to the first, or I need to work on my terms here, a sub 1, which is my first term, so I get 3 times 1 on top and 1 plus 5 on the bottom. So 3 times 1 on top is 3, 1 plus 5 is 6, and I always reduce to lowest term, so a sub 1 is 1/2. A sub 2, so I'm going to take 3 times 2, because it's my second term, and 2 plus 5, and I get 6/7, and that one doesn't reduce, so I leave it as is. A sub 3, there is my third term, so I get 3 times 3 on top, and 3 plus 5 on the bottom, and I get 9/8, and you'll notice I'm now a mixed number or improper, but once again it's reduced to lowest terms, so I'm going to leave it. And a sub 4 is going to be 3 times 4 over 4 plus 5, and I get 12/9, and this one does reduce by 3, so I get 4/3. And again, so my actual answers are my four terms here, 1/2, 6/7. That was not a good box, but you know what? That's what it's going to get, 9/8 and 4/3. Okay, so those are my answers there. Okay, so that's a finite series. So let's come down here and do some recursion formulas. Okay, sounds kind of fancy. A recursion formula defines the nth term of a sequence as a function of the previous term. Okay, so what we're actually going to do is use the term before it to get the next term. That's why it's recursive, because it uses the one in front of it. Okay, so when you see these recursive formulas, you're going to notice that they're going to give you the first term usually, or at least a term in the sequence. Okay, So my first one they do give me a sub 1 equals 4. So if I'm writing the first 4 terms, I actually have the first one, okay? So my first one is just a sub 1 equals 4, so there's one of my answers, okay? And now I'm going to find my second one. So here's my formula, and you'll notice that n needs to be greater than or equal to 2. So for my second term, I'm going to do a sub 2 because it's my second term, and it says 2 times a, and I put 2 minus 1 down here, plus 3. Okay, so a little simplification. If I do 3 minus 1, that actually makes, I'm sorry, it's 2 minus 1. 2 minus 1 will make 1 plus 3. Well, here's my a sub 1. I already know a sub 1, so I'm going to replace that a sub 1 with the 4 from before and then add 3. 2 times 4 is 8 plus 3 is 11. So my a sub 2 is 11. I had to use the term before it to be able to find it. Okay, so now when I work on my third term, my a sub 3 is 2 times a to the 3 minus 1 as I plug into my formula, plus 3. Okay, so if we think about this, 3 minus 1 is 2, so that gives me an a sub 2 plus 3. So I get 2. I go to my a sub 2 that I found earlier, which is 11, and now I add my 3. So I get 22 plus 3, and my a sub 3 is going to be 25. Okay, so a recursion uses that term in front of it. Okay, I am going to see if I can squeeze my a sub 4 in here. I'm actually going to probably come across the bottom, so I know I can. So for my a sub 4, I'm going to do 2 times my a sub 4 minus 1 plus 3. So I'm going to get 2 times a sub 3 plus 3. When I look back up at my a sub 3, it was 25. So I replace a sub 3 with 25. And I'm going to get 50 plus 3. So my a sub 4 here is 53. So this is a recursive formula where you use one of the terms before. Now, I showed a lot of work here. If this is something you can look and go, oh, it looks like I'm just going to do 2 times the term in front of it plus 3, you may do a lot of this in your head, but don't be afraid to write them out until that makes sense what's going on there with that recursion formula. All right, let's turn the page and find some more fun. All right, so at the top of this page, we're introducing a factorial notation. Factorial notation, n is a positive integer, and the notation n with that exclamation point, we actually read it n factorial. And it means it's the product of all positive integers n, notice this is positive, down through 1. So if I just gave you a scenario and I said it was 25, n was 25, that means you do 25 times 24 times 23 times 22 times 21 times 20 times 19 times 18 times 17 times 16 times 15 times 14 times 13 times 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, and we always stop at 1. You do not want to multiply by 0. And I do want to point out here that if you get a 0 factorial here, 0 factorial is always 1. So we will not be multiplying by a 0 anywhere along the way. So this is something that as you work with factorials, and yes, they are used, we will actually use them quite a bit here in this chapter when we start working on some combinations and permutations and things such as that. You're trying to figure out how different things can work and how many different ways they can work. I copied from the book this chart over here, this factorial chart, and you'll notice, it starts small. 2 factorial is 2, 3 factorial is 6, 4 factorial is 24. I started at 25, and I struggled just to say all the numbers all the way down. Notice down here at 20 factorial, that value of 20 factorial, if I can remember my place values, thousands, millions, billions, trillions, quadrillions, quintillions, 2 quintillion, and some change there for 20 factorial. It gets big fast. In fact, this is a faster growth than you would see with exponential, when you had like 2 to the x value or something like that, to the x power. We know that grows quickly, but this grows even faster with a factorial. So to start out with, we're just looking at, can we operate with factorials today? And later in the chapter, we'll actually use factorials more, combinations, and some probability things. So On a quick side note, I'm going to be honest, when I learned factorials, I learned them. I said, who uses them? I have a brother that works in logistics at UPS, and he said he does use factorials some when they try to find a combination of how many different ways they can run a truck through the routes or whatever to do their deliveries. So it is something that, in a business sense, it can be used. So we're throwing it out here so you know it, and of course someday it might be programmed in a computer, but it's nice to know what's programmed and how that program might be working. Okay, so now that I'm off my tangent, let's go ahead and figure this out. For number 4, it says the first four terms of this sequence. And once again, we're just going to go through and use our notation. So on the left side, this is our order, our a sub 1. And you'll notice what I do when I fill in here. This time I have 1 plus 1 factorial over 1 squared. So 1 plus 1 is 2. And this is really a bad thing, I guess. 1 squared is 1. 2 factorial, that's 2 times 1. That's the same thing as just 2. Divided by 1 is 2. So a sub 1 is going to be 2. And I can see right away I'm going to struggle to write small enough and write all this in here. All right, so let's try our a sub 2. So our a sub 2 is going to be 2 plus 1 factorial over 2 squared. All right, 2 plus 1 is 3 factorial over 4. Okay, so 3 factorial, 3 times 2 times 1 over 4. You can use the chart. I wouldn't be bad as you're starting this out to just work through them so you can kind of see it visually what's happening. So 3 times 2 is 6, times 1 is 6, divided by 4. I get 6/4 or 3/2 when I reduce that to lowest terms. And that's my a sub 2. Okay, a sub 3. I get 3 plus 1 factorial over 3 squared. So I get 4 factorial over 9. To save myself some time, so 4 times 3 is 12, times 2 is 24, times 1 obviously is still 24. So I get 24 over 9, and when I reduce that, my a sub 3 can be 8/3. You'll notice as you look at these answers, it's not like you can look at one answer and necessarily see what the next answer is going to be. Very much different than if you remember sequences, you know, when you're like, well, they add 2 every time or something like that. This one's a little more complicated. So a sub 4 here, I'm going to get 4 plus 1 factorial over 4 squared. So that's a 5 factorial over 16. 5 factorial, I'm going to cheat and use the chart right here, 120 over 16, and that is going to reduce to 15 over 2 when I divide by 8. All right, so that's, again, a finite series, or I should say a finite sequence there, and we stop at the 4th one. All right, excuse me. Our next one, evaluate this factorial expression. Notice I have 20 factorial over 2 factorial times 18 factorial. Huge numbers if I look at the chart. So let's just think about what this means. 20 factorial over 2 factorial times 18 factorial. Okay? 20 factorial, that means 20 times 19 times 18, and I'm going to stop, and so on, right? 18 factorial. 2 factorial is like 2 times 1. I'm going to leave 18 factorial. Okay, so this is how I rewrote it. I haven't changed the value of anything. I started to write out the top 20 times 19 times 18 times 17 and such. On the bottom I wrote 2 times 1, and I left the 18 factorial. And the reason I did this is we have a fraction, and with a fraction you can always reduce common terms from top to bottom, common factors, and I have a common factor. I have an 18 factorial on the bottom, I have an 18 factorial on top. I can cancel those. So if you have a huge factorial and you notice that you have a somewhat equally big factorial that you're going to divide by, there's no sense in making those numbers huge and then trying to figure it out or get that calculator. I'm going to be honest, it's really hard to take that number for 20 factorial and plug it into your calculator. It's more numbers than the screen can take. So just keep that in mind, that if we can do some simplifying by hand, that's better. Okay, I have one more simplifying I can do. I know 20 can divide by this 2, and I can change that to a 10. I'm left with 10 times 19 on top. I'm left with 1 on the bottom. I easily can do that math in my head and get 190. So sometimes these factorials are better to be done without a calculator, okay? All right, summation notation. So it is super important to realize basically what this is just saying here, summation, okay, sum. We're going to add, okay? So when you see this symbol here, this summation, it kind of looks like it's the Greek letter there for a summation there. And we have different parts of it, okay? The index is down here on the bottom. The index of summation basically tells us where do we start? What's our starting point for our index? Then on top, you have the upper limit. That means where are we stopping at, okay? And in this case, 1 is my lower limit because that's where I started at. That's my index where I'm going to start from, and I go from there. So on this one, I is the index. You'll notice right away on 6 and 7, K, or I shouldn't say that, on 6, K is the index. So it changes. But again, it tells us what's our starting thing we plug in and what's our ending one we plug in as we work through these. So we actually have what would be a sequence, but we're going to start and stop it at a certain point. And then, because it's a summation notation, we're going to add all those answers together. Okay, so if you think of looking back up there, and I'll be honest, on number 4, with those kind of fractions, they would not be fun to add them all together, though we could with a common denominator. But we're still finding our 4 or however many terms it is, and then we're going to add those together because it's the summation of them. Okay, so on number 6, I'm going to start there, and again, hope for small writing, but I know that's not always the case. So my index says K equals 1, which means I'm going to start with 1 and plug it in, and I'm going to go up by 1 integer at a time until I get up to the 4. So for my K equals 1, okay, and I'll just kind of code it like this so I know. So I get 1 minus 3 times 1 plus 2. That is 1 minus 3 is negative 2 times 3, and I get negative 6 for my first term. All right, second one, K equals 2. That means I get 2 minus 3 and 2 plus 2. I get a negative 1 times a 4, and I get a negative 4. Make sure I write that clearly. Negative 4, wow. All right, K equals 3. So I get 3 minus 3 times 3 plus 2. That gives me a 0 times 5, which is just simply 0. And I'm still going because it says my upper limit is 4, so I go to 4. And I'm going to get 4 minus 3 times 4 plus 2. That gives me a 1 times a 6, and I get a 6. But again, this says find the indicated sum because I'm on a summation, which means I'm going to take all these answers, these 4 answers, from the first to the 4th, and I'm going to add those together. So negative 6 plus negative 4 is negative 10, plus 0, still negative 10, plus 6 makes negative 4. So my answer here for my whole thing is negative 4. Yes, I need to have all that work to find it, but my final answer is simply the sum of my answers. All right, let's look at number 7. Notice we pull the factorials back in here. I'm going to kind of start in any blank space I can find. Notice this time my index starts at 1 and it goes to 5, so I'll have 5 terms in here before I do my summation. So when I start off with I equals 1, I have 1 factorial on top over 1 minus 1 factorial. So that gives me 1 factorial is 1. I get 0 factorial, which is also 1. So I just get 1 for that first answer. Okay, I equals 2. So I have 2 factorial over 2 minus 1 factorial. 2 factorial is 2 times 1, which is 2. 2 minus 1 is 1 factorial, which is just 1, and I get an answer of 2. So for my third term, I get 3 factorial over 3 minus 1 factorial. This is the same as 3 factorial over 2 factorial. Well, remember, if we use that trick where we go 3 times 2 factorial and then 2 factorial, they'll cancel, and I'll just be left with the 3. If somebody's not just looking at these and not listening, that's going to be confusing how I just went there, I think. Then I get 4 factorial over 4 minus 1 factorial. So that's the same as 4 factorial over 3 factorial, which remember is the same as 4 times 3 factorial over 3 factorial, which means that I can just cancel and get 4. And finally, my fifth one is going to be 5 factorial over 5 minus 1 factorial, which is 5 factorial over 4 factorial, which means my 4 factorials cancel, and I'm just left with 5. So now my summation is all my answer is 6 plus 4 is 10 plus 5 is 15 for my summation. So don't forget on those, when you see that summation, your answer should be one number. Is it always positive? No. Number 6 showed us that. So don't think just because your index is positive and increases by positive intervals that your answer will always be. So depending on the operation that you end up doing, you can have negative sums. All right, last and final one. Express the sum using summation notation. Use 1 as the lower limit of the summation and I for the index of summation. So what you see here is the pattern. They're showing you the pattern. I have a 1/3 plus 2/4 plus 3/5 plus something, something, something until I get up to 16 and 16 over 2. Now, as much as that can look confusing, like what's going on, I'm going to give you a big hint. You really want to watch the very last term because it gives you the most hints as far as what's happening here. So we know we're starting with a summation. Do your best to draw that. And it tells us that 1 is my lower limit, I is the index, so I'm going to start with I equals 1. And if I think about it, if I equals 1, and I see that my first fraction started with a 1 on top, and my last fraction starts with or ends with a 16, how many terms do you think I went through to get from 1 to 16? Since I notice on top I'm going up by 1, 2, 3, something, 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 so many, we're not sure how many, I end with 16. It makes sense to say that I'm going from my first term to my 16th term, okay? So as I start my rule, I'm going to try to keep my rule as condensed as possible. So I think I'm just going to put I on top because if my first term is 1, my second one has a 2, my third has a 3, my 16th has a 16, it makes sense that I just put I on top for my rule. Okay, so how can I now put my bottom so that I can get what I need? So on the last term, I see 16 plus 2. So I go back to my first term. If I think of 16 plus 2, if that was like I plus 2, is my 1/3, is that really 1 plus 2? Sure, 3 is 1 plus 2. On the 2/4, is that really 2 plus 2? Sure. 3 over 5, is that really 3 plus 2 on the bottom? It definitely is, which means it looks like I'm taking my index again and adding 2 each time for my denominator. Now, they were super nice to us and they didn't reduce that 2/4. If they had reduced it to 1/2, it might have been a little harder to see that pattern. So when you're writing these patterns, hopefully they will keep them written out there. And again, am I going to have you do a lot of those? Probably not too many, but it's good to kind of see, can I write this? Are there other ways to write that? Yes. Okay. Just like we had that in last chapter when you were taking and writing those parameters, parametric equations. There's infinite number of ways you can write this. Of course, it's easiest for us to stay in a very simplified manner. Okay. That's it. That's our lesson. Okay. So if you want to practice here, I seem to be missing it here, but I would look on page 960 in your text and anywhere from the 3 to 60s by 3s or by odds so that you can look them up in the back of the book, something to that effect, that you can practice just working through some of these sequences and finding the next terms, some of the summations. Don't forget to add those terms together. Have fun.